15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again. Thank you for joining us on Space Nuts. It's so good to have your company. I'm your host, Andrew Dunkley, and I hope you're well. Today's program's a little bit different. We will not be venturing into the universe through new knowledge that's been published or talking about space rocket launches that have happened in recent times or asteroids that have, hit us and killed us all. Don't think that's happened. What we're doing today is dedicating the show to the audience. Once in a while, we throw it over to you to throw at us some of the questions you want answered. And so that's what we're going to be doing today. Questions about the ultimate fate of the universe. I think I know the answer to that one, and it's going to happen next week. Cepheid variables is a question we've received. What is that, and what does it cost at the supermarket? Can we use magnets to protect spacecraft heading to Mars, or anywhere for that matter, I suppose? Can asteroids that come close to Earth change our orbit? And a question we've received from Paul in Queensland, and he's put it all in song. And I think it's a ukulele that he's backed up with. It's brilliant. We'll give you that. And the movement of stars in our galaxy, all of those questions we will answer today. And if we can't answer them, we'll make it up. On Space Nuts. And joining me, as always, is Professor Fred Watson, Astronomer at Large. Hello, Fred.
Andrew. We're pretty good at making things up, you and I, actually.
It's one of the things they teach you in journalism school.
Make it up.
The segment is called "Never Let the Truth Get in the Way of a Good Story." So it's everybody's favourite thing when they go to school to learn about broadcasting and journalism. Yes. We've got a whole bunch of questions to get through today, Fred. So we might as well get straight into it if you're ready.
Yep.
Okie dokie. We'll go first to Mark.
Hello, Space Nuts. Martin Berman Gorvine here, the science fiction writer who asked you recently about the non-existent luminiferous ether. Today I'm wondering about the ultimate fate of the cosmos. Will it continue expanding infinitely until everything is very cold and very thinly spread, as imagined in classic science fiction tales such as John W. Campbell Jr.'s Night and my own Tricky Dick Nixon and the Heat Death of the Universe, which is available on Amazon? Or is there any chance that instead of freezing to death, we're all going to crunch up in a super hot collision as everything snaps back like a universal rubber band and collapses into a singularity and maybe explodes again in another big bang ad infinitum? It's my impression that the cold soup scenario is now thought to be more likely, but what is the real evidence, and might opinions change again? Thanks for taking my question.
A great pleasure, Mark. Lovely to hear from you again. And yes, it's one of the most popular questions that gets asked of astronomers. Fred, what's going to happen to us all? Is the end nigh? Well, probably not, but it's going to happen eventually. But how will it end? Will it just become a big frozen ball of nothing, or will it, will the Gib happen, the reverse Big Bang, and just crush in on ourselves in a flaming end? It's a question that surfaces quite often.
Yeah, and actually, Mark has already given us the answer in the title of one of his novels, which included the term "the heat death of the universe." And it's interesting that was a term that was popular when I was a youngster. Kind of before I became an astronomer, people talked about the heat death of the universe. The idea
that was back in the late 1800s, wasn't it, Fred?
It wasn't that long after that. No, the late 1800s always seemed quite recent to me when I was growing up, believe it or not. That's more to do with where I grew up, I think, which had its feet firmly planted in the late 1800s, including the school I went to. Anyway, all of that's irrelevant. But it's essentially the heat death of the universe is the idea that the universe just cools down and basically fizzles out. So for a period during the 70s and 80s, there was a much different idea, a more popular idea, that maybe the universe, which was known already by then, of course, to be expanding, that was discovered in 1929, that the universe might slow down in its expansion because of the gravity of everything within it, and eventually stop expanding and start collapsing on itself to produce what you and I have discussed before, the Big Crunch, which was also christened by Brian Schmidt, the Gnab Gib, which is the Big Bang backwards. Fantastic stuff. I love to get that in anything I can when I talk about it, the Gnab Gib. So the idea was that, yes, maybe it would collapse back to another singularity, which would sort of bounce. Maybe the expression "the big bounce" was sometimes used, so that you get another expansion from this rebound of the universe. What put the nail into the coffin of that idea, the final nail, was once again Brian Schmidt, the professor of astronomy as he then was at the Australian National University. Now in fact it's vice chancellor. So the discovery made by Brian's group and another group in the USA, led by Saul Perlmutter, those two groups independently demonstrated that the universe is expanding at an ever increasing rate. So it's accelerating. And we think that's because of dark energy, which we don't understand. And so what we've got now is a scenario where, to the best of our understanding, the universe will simply continue expanding at an ever-increasing rate, unless something changes. But what that might be, we have no idea.
Maybe bumping into another.
Well,
universe.
That's the sort of thing. But at the moment, that's so far beyond our knowledge horizons that we really can't do anything about it, or even build it into our ideas. So at the moment, the idea is, yes, that the universe will continue to expand at an ever-increasing rate. And so the fate of the universe is not pretty. I might actually make it easy on myself by reading from the new book, Space Warp, because I've got a little section on the fate of the universe, which says, if the accelerating expansion continues as it's going now, there will come a time billions to trillions of years down the track when distant galaxies start disappearing. That's because the light leaving them will never reach us, since the space between them and us is expanding too fast. Astronomers in the far distant future will only be able to study our Milky Way galaxy and its fellow members in the local group. To them, that will be the whole universe. And to make matters worse, the universe's hydrogen supply will have been exhausted, so no new stars will be formed, while the existing ones will eventually die and turn into black dwarfs or black holes. But even that isn't the end of this dark and gloomy story. This is to cheer up the youngsters who read it, Andrew.
Yes, this is a children's
yes,
book, isn't it?
There's better news after the end of this section. Eventually, space will be expanding so rapidly that galaxies, stars and planets won't be able to resist its power to tear things apart. They will be spaghettified as if they were falling into a gigantic black hole. And the final insult, as it is an event usually called the Big Rip, in which atoms, subatomic particles, and perhaps even space-time itself will disintegrate. As I said, it's not pretty and basically has all the hallmarks of a gigantic temper tantrum. Not nice behaviour for a polite universe. Fortunately, it is so many billions or trillions of years in the future that it really doesn't matter.
And who knows where humanity will be then, if it exists
at all. That's right.
Yeah. So it's not going to be a pretty end, Mark, I'm afraid to say.
As far as we know.
as far as we know. But I suppose the thing that is difficult to get my head around and most people's heads around is how could the universe possibly continue to expand at an accelerating rate? It just doesn't seem logical.
It's yes, and dark energy isn't logical, which is why we really don't understand it. So the idea of dark energy is that it's a product of space itself. So the more space you've got, the more dark energy you've got, and that pushes it, apart even faster. So it's like what you might call a positive feedback. It just kind of keeps on going and eventually produces effectively an exponential expansion.
It's like a giant fusion reactor. It just keeps feeding itself.
Yes, except there's no fuel and no need to convert anything into anything else. It just comes from space.
Yeah, it's so strange.
Work that one out.
It's so strange. I can't. If you can't figure it out, what hope have I got?
So it's possible that our idea of what dark energy is like is wrong, and that it's not a property of space itself, that it's some other fundamental force, and one that people talk about is called quintessence, a fifth fundamental force. If that's the case, then it might behave in a different way. It may get quenched when the universe gets to a certain size, or who knows what could happen. But based on what we know so far, the end I've described is what might well happen down the track.
And somewhere along the line in that process, it's going to get very cold and dark.
Yeah, because there's nothing left. Stars eventually die. They all die out. There's no hydrogen left to form new stars. So it becomes cold and dark. Yeah.
And so it's just going to be a whole bunch of dead rocks floating around.
More or less. That's right. Getting further and further apart. It's boring, isn't it? Really?
How exciting.
Yeah. The Big Rip's a lot more exciting. Everybody would be having their Big Rip party. Sorry, the Big Crunch, I beg your pardon. The Big Crunch will be a lot more exciting, yeah.
But at least we all get to go to the restaurant at the end of the universe.
Exactly, that's right.
Exactly. Hitchhiker's Guide to the Galaxy, for those who are going, what on earth is he talking about? In fact, people say that to me every week.
Yes, whether you're talking about that or not.
Indeed. All right. So there you are, Mark. You asked, and you probably don't like the answer, but nothing much we can do about it at this point in time. And you did say that the space-time might unravel, which means time would end, wouldn't it?
Well, probably, yeah. It probably falls to pieces. So as time gets fragmented into little chunks. Now, how do you deal with that? I have no idea.
You have to wear 50 million watches, I suppose. I don't know.
Might have to.
No idea. No idea. Okay, thanks, Mark, for the question. Now let's move on to our next inquisitor. And this is Paul from Pennsylvania.
Hello, Fred and Andrew. This is Paul from Pennsylvania. I have a question about Cepheid variables. I know Leavitt discovered that they were variable, and Hubble used them to discover the distances to galaxies. I was just wondering exactly how that worked. Never seemed to be able to get a straight answer on that. Thank you. Bye.
All right. Cepheid variables.
Yes, they are they're fundamental in our understanding of the distances to galaxies, particularly. So, and it goes right back to Hubble's time, exactly as Paul says. So
one of your old classmates, wasn't he?
I wish. He was a bright spark, that lad. But it was actually a woman who discovered the fundamental issue here back in 1908. Henrietta Swan Leavitt, who Paul mentioned, she looked at many thousands of stars in the Magellanic Clouds. These two, as we now know them to be, nearby dwarf galaxies. And the thing about studying variable stars is if they're all in one place, as these were in the Magellanic Clouds, then you know that they're all effectively at the same distance, which we now know is, I've forgotten these numbers, 165,000 light years for the Large Magellanic Cloud. So they're all the same distance away. And so any changes in their brightness is intrinsic. It's not caused by coming backwards or forwards or anything like that. They're all sitting in this Magellanic Cloud, and they're all varying with different brightnesses. That's what a variable star is. It's one whose light output varies over time. So she could watch these things and make the observations. And the discovery that she made was that Cepheid variables, first of all, are periodic. Their variation in light actually, it's regular, but they don't all have the same period. So their periods range typically up to 60 days or something like that. Somewhere between 10 and 60 days will be a typical time for the period of a Cepheid variable star. But what she discovered was that the ones that vary over longer timescales are actually brighter. And they're brighter intrinsically because they're all at the same distance. It's not a distance effect that she's confusing it with. The longer period Cepheids are brighter. And Henrietta Leavitt was able to essentially plot a diagram that shows the relationship between the period of variability, how it goes up and down, how long it takes to go through one cycle, and the brightness. And it's called the period luminosity diagram. It's actually the fundamental thing. So what it means, Andrew, is if you find a Cepheid variable in the sky, all you've got to do is to measure its period, how long it takes to go through one cycle. You then look up Henrietta Leavitt's diagram or its modern equivalent, and that tells you how intrinsically bright it is. And if you know its apparent brightness, as we observe from Earth, then that gives you its distance very accurately. And that's how it works. So it was when Hubble detected Cepheid variables in the Andromeda galaxy, which he would have called the Andromeda Nebula because he didn't know it was a galaxy, he was able to plot the distance very exactly. In fact, they got it wrong because there was an error in the calibration of the Cepheid variables, but that was fixed later. So that is the step, and that's what allows you to start measuring the distance to galaxies. It's that fundamental step in what we call the distance ladder. And actually, it is the reason why the Hubble telescope was built and launched and used, was to make very accurate measurements of Cepheid variable stars in other galaxies to work out what the calibration is for distant galaxies.
The only thing I can think of in that regard is, with everything constantly moving, wouldn't there be constant variation in the calculations and the results? Or am I
things are moving, but only on the distances through which they move are tiny compared with the distance away that these stars are. So it doesn't actually make any difference to the brightness. If they were whizzing away and their distance was changing by a factor of 2 or 5 or 10 or whatever over a short time, yes, that would make a difference. But no, it was doing them in the Magellanic Clouds that was the clincher, because that they're all 165,000 light years away. Yes, the clouds have got, or for the large cloud, the clouds have got their own thickness, but it's tiny compared with the distance to it. Yeah. So very, very clever stuff.
Yeah, fascinating. Way beyond my pay grade, definitely.
Well, it's probably beyond Henrietta's as well. So because she started off as one of these computers, one of these people who just measured the brightness and positions of stars. But she became a pivotal figure in 20th century astronomy.
Yeah, quite astute by the sound of it.
Absolutely.
All right. Thank you for the question, Paul. Great to hear from you, and nice to get something completely different. We've never really discussed that before, so good for you. You're listening to, and if you're a YouTuber watching, I don't know why you'd want to see our faces, this Space Nuts with Andrew Dunkley and Professor Fred Watson.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.